An A36 steel bar is constrained to just barely fit between two fixed supports when the temperature is 60 degrees Fahrenheit. Now, one thing to note is it just barely fits in there, which means that there is no force being applied. We can slide it in and out. If the temperatures are raised to 120 degrees Fahrenheit, determine the average normal thermal stress developed in the bar. Modulus of elasticity of A36 steel is 29,000 kips per inches squared, or 29,000 KSI. So just a note on this picture, we're showing this bar standing up. This ½ inch by ½ inch is the cross section of the bar. So all the thermal stress is we have increased the temperature of something, so now it is pushing against the wall, so it's causing a force. So if I draw a free body diagram of this after things have gone, and let's actually not use red. If I draw my free body diagram of this guy here, well, what's going to happen is it's going to grow. I'm going to have a force that's being applied here at A. I have a force that's going to be applied here at B. If I do my statics equation, we'll say sum of the forces in the y upward is positive. That's going to tell me that FB minus FA is going to be 0, or just FB is equal to FA, and that doesn't help us. It's just that is the force that's being applied. So we have a statically indeterminate problem. Now this statically indeterminate problem is a little bit different than the other ones that we've done because we are not applying any external loads on this. We have nothing going on. We have the thermal load itself that's applying everything. So what we'll do is let's write a compatibility equation for this. Once again, you can solve this using either the method of superposition or the method of kinematic equations or compatibility equations. It doesn't matter to me. This one I'm going to solve using compatibility equations. So I know that the deflection between A and B has to be equal to 0. So if I know that has to be equal to 0, I have my thermal deflection minus my deflection from the forces has to be equal to 0. So what do? Well, we just go and we figure those out. So I know my deflection from the force is going to be equal to PL over AE. It's one cross section. We just have one force on it. That's all it's going to be is PL over AE, which P is what we're looking for. And I know that my thermal deflection is going to be alpha delta T times the initial length. So what are we going to have to do? First thing we got to do is we need to go get some information. Now, in the problem, I told you what the modulus of elasticity was for A36 steel, but I did not give you what the coefficient of thermal expansion is. So what do? We go take a look up in the book. I'm fairly certain that you will not find this in the engineering equation manual because it is not an exhaustive list of all the materials. Although A36 is pretty common, it might be in there. But if you go to your textbook and look it up, we can find the coefficient of thermal expansion for A36 steel is 6.6 times 10 to the negative 6 per degree Fahrenheit. And so there's our thermal expansion. So what we can sit there and do is, once again, I know that thermal stress minus the force stress, thermal deflection minus the force deflection has to be equal to 0. So 0 is going to equal alpha delta TL minus PL over AE. I've got an L in all these things. What am I going to do? I'm going to divide everything by L. If I divide this by L, it goes away. Divide this by L, it goes away. I divide 0 by L, well, it's the mathematical black hole. That's going to fall out too. So what I'm going to be left with is 0 is going to be equal to alpha delta T minus P over AE. Then we can plug in all of our numbers there and figure out what's going on. In fact, since 0 is on the other side, let's just rearrange this equation. I'll move P over AE to the other side. That's going to equal alpha delta T. And then just multiply through. So P is alpha delta T times AE. So everything's there. We can just plug numbers in and calculate. 6.6 e to the negative 6, 1 over degree Fahrenheit. Delta T, we've got 120 degrees Fahrenheit minus 60 degrees Fahrenheit. That's a positive number. It's increasing. We expect it to get longer. We'll pop just down to the next line here. So we've got the area. Now, it's a ½ inch times a ½ inch. So we'll just do a ½ inch squared times 29e to the 3 KSI, kips per square inch. So kips per inch squared. So the inches squared will cancel out. The degree Fahrenheit will cancel out. We're left with kip. And so that's just going to be 1,000 pounds. And so when I go and calculate that, my P is going to be 2.871 kip, or 2,871,000 pounds. That's not the answer, though, because remember, it asked us, what is the internal stress? How do we find stress? Thermal stress is going to be that thermal load. So we'll say PT for thermal load divided by the area. 2.871 kip divided by an area of 0.5 inches. We've got two of them, so we'll just square that. So 0.5 inches times 0.5 inches. And that'll give us 11.5 thousand pounds per square inch, or 11.5 KSI. So that's our thermal stress. That's the answer to our problem. Notice lengths canceled out. Didn't really have to worry about the length because of the way the bar was set up. If the bar had a change in area in there, yeah, we'd have to write two equations because we'd have a change in area, or if there are two different materials or whatnot. But as it is now, that falls out. That's why we write the equations out first.